Partition Equal Subset Sum. This problem looks innocent. And then Rex timelines. Partition Equal Subset Sum is a pattern mastery 100 star, because it tests whether you can recognize a hidden subset sum dynamic programming problem and reason about time-space trade-offs on the fly. Good news! With a basic framework and a slick 1D DP, you'll narrate and code this confidently, no brute force backtracking meltdown. Breakdown. We get an array of positive integers called nums. Can we split it into two subsets with equal total? If the total sum is odd, the answer is immediately false. Otherwise, we just need to know whether some subset sums to total divided by 2, classic subset sum. Assess. Backtracking is exponential. Instead, we use dynamic programming. Define dp of s as can we make sum s using the numbers we've seen so far? Initialize dp of 0 as true. For each number x, update dp of s by checking dp of s minus x, going backward from target down to x, so we don't reuse x multiple times. The complexity is O of n times target in time, and O of target in space, where target equals total divided by 2. A neat alternative is a bit set that shifts reachable sums with bits OR equals bits shifted left by x. Structure. Compute the total. If it's odd, return false. Set target to total divided by 2, and create dp of length target plus 1 with dp of 0 set to true. For each x in nums, iterate s from target down to x, and set dp of s to dp of s or dp of s minus x. Return dp of target.
Let's try to implement it using solution 1. We begin by defining the solution class. This is the wrapper for the method we're about to explain. Then we declare the canPartition method. It takes an array of integers and determines whether it can be split into two subsets with equal sums. We set up a variable called total to accumulate the sum of all elements. Next, we loop through every number in the array and add each one to total. This step runs in O of n time. After that, we check whether the total sum is odd. If it is odd, we cannot split it into two equal halves, so we return false immediately. Now we compute the target sum, which is total divided by 2. This is the sum we want one subset to reach. If one subset reaches target, the remaining numbers will also add up to target. We create a Boolean dynamic programming array called dp with a size of target plus 1. dp of s will be true if we can form the sum s using some subset of the numbers. We set dp of 0 to true. A sum of 0 is always possible by choosing no elements. Next, we iterate through each number in the input array. Each number helps us update which sums are now reachable. Inside that loop, we iterate s backward from target down to the current number. We go backward to make sure each number is used at most once per update pass. For each sum s, we check dp of s minus num. If dp of s minus num is true, then adding num makes dp of s true. That is the key dynamic programming update. Finally, we return dp of target. If it is true, we successfully formed half the total sum and can partition the array into two equal subsets. And that's how this algorithm works. It computes the total sum and determines the target half. Then it builds a dp table that tracks all achievable subset sums. At the end, it checks whether the exact halfway sum is possible, efficient, simple, and elegant. Check. This test examines the partition equal subset sum problem. The input array contains 1, 5, 11, and 5. First, compute the total sum. 1 plus 5 plus 11 plus 5 equals 22. Since 22 is even, a partition is possible in principle. Each subset must sum to 11. Now check whether any subset can form the target sum 11. One valid subset is 11 by itself. Another valid subset is 5 plus 1, which equals 11. Because the target sum is reachable, the array can be partitioned into two subsets with equal totals, so the correct output is true. The output is true, matching the expected true. This confirms the solution correctly identifies that an equal sum partition is possible. Now let's try another implement approach using solution 2. We begin by defining the solution class. This is where we store both the method and a memo table that speeds up the search. Next, we create a memo map. It remembers results for a pair of values, the current index and the current running sum. This prevents solving the same subproblem more than once. Then we define the main method, canPartition. It determines whether the array can be split into two subsets with equal sums. We set up a variable called total to hold the sum of all numbers. Next, we loop through the array and add up every element. This step runs in O of n time. After that, we check whether total is odd. If the total sum is odd, it is impossible to split the array into two equal whole number sums, so we return false immediately. Otherwise, we begin a depth-first search. We start at index 0, with a current sum of 0, and our target sum is total divided by 2. Now we move into the recursive helper function. This helper explores whether we can form the target sum using the remaining numbers. First, if the running sum equals the target, we have succeeded, so we return true. Next, if the running sum becomes larger than the target, we stop this path. Also, if we have reached the end of the array, we stop this path. In either case, we return false. Then we build a key that uniquely identifies the current state. It combines the current index and the current sum. Before doing more work, we check the memo table. If this state has been solved before, we return the stored result immediately. Now comes the branching step. In the first branch, we include the current number and recurse to the next index. In the second branch, we skip the current number and recurse to the next index. If either branch returns true, then this state is successful. After we compute the result, we store it in the memo table. That way, any future call with the same index and sum can reuse it. Finally, we return the stored result for this state. And that's how this algorithm works. It first checks whether the total sum can be split evenly. Then it uses a memoized depth-first search to explore subset combinations. The memo table avoids repeated work and keeps the search efficient, simple, and elegant. Check. This test verifies the partition equal subset sum logic when a valid partition is not possible. The input array contains 1, 2, 3, and 5. First, compute the total sum. 1 plus 2 plus 3 plus 5 equals 11. Because 11 is odd, it cannot be split into two equal whole numbers. Half of 11 is 5.5, and subset sums must be whole numbers. So an equal partition is impossible, no matter how the numbers are arranged. Therefore, the algorithm correctly returns false. The output is false, matching the expected false. This confirms the solution correctly, identifies that an equal partition is not achievable for this input array.
Let's have a quick recap. Breakdown recap. So, wrapping this up, partition equal subset sum asks whether we can split an array into two subsets with the same total. It sounds simple, but the key is recognizing that it is actually a subset sum problem in disguise. If the overall sum is odd, the answer is immediately impossible. If the sum is even, the real question becomes whether there is a subset that adds up to half of the total. Assess recap. We compared approaches and saw why brute force fails. Backtracking grows exponentially and becomes unmanageable very quickly. Dynamic programming, on the other hand, gives us structure and efficiency. By tracking which sums are reachable as we process each number, we convert the problem into a predictable O of n times target solution. There is also a bit set trick that accomplishes the same idea using fast bit shifts. Structure recap. The plan was straightforward. First, handle the odd sum rejection. Next, set the target to total divided by 2, create a DP array, and for each number, update reachable sums from right to left. This backward update prevents reusing the same number twice and ensures that our DP remains correct. Implement recap. During implementation, we built a one-dimensional DP table that expanded as we processed each number. The logic stayed clean. Start with DP of 0 set to true, then mark all newly achievable sums. Memory usage stayed low, and execution remained tight, which fits interview constraints very well. Check recap. When tested on multiple arrays, every case behaved exactly as expected. Valid partitions returned true, and impossible ones returned false. Both the DP and the bitset variants produced matching results, confirming that the algorithm is both efficient and reliable. The key takeaway is that many problems that ask you to divide or split arrays are actually subset sum patterns in disguise. Recognizing that structure early turns what looks like a complicated recursive challenge into a simple and elegant DP. This problem is a great reminder that understanding patterns is more powerful than memorizing solutions.